So in section 1.6, exercise 6, let's take a look. So we have positive integers, m and n, and the GCD, greatest common divisor of m and n, is, let's call it d. And we want to show that this is the largest natural number, positive integer, dividing m and n. So sometimes one might define the greatest common divisor of two numbers to be the largest number that divides both of the integers. But for various reasons that you see later, an equivalent definition and a better definition is the following. So D is the GCD of m and n if it satisfies two conditions. First, D divides m and D divides n. And also we want it to be a natural number, a positive integer. So we take the positive integer d, it divides both m and n, and if x divides m and n, then x divides d. So this is the definition. So, well, but if x is greater than or equal to 1, and if d is greater than or equal to 1, and x divides d, then d is x times q for some q greater than or equal to 1. That's what divisibility means, which means if d is x times q, and q is at least 1, then d is greater than or equal to x. And we're done. So this says that if you take any common divisor of m and n, it's less than or equal to d. So d is the largest one. That's the whole proof. All right. So you have to think about this a little bit, but what I wrote is really all that you need to say. Right. Any questions about this?
No.
Okay, and then you also asked about exercise 9.
Yeah.
So 9 uses a lemma in the text that I'll review today, I'll repeat today or prove today. So we have a following lemma. Let me just find it actually written down exactly. Well, so in the text, what is corollary 1.620 on page 33 says that if P divides a product, so this is actually, the exercise is to prove this corollary, but the corollary is a corollary to a certain proposition that comes right before it. So proposition 1.619. And what prop 1.619 says if P divides, that's what a vertical line means, A times B, A and B non-zero, then P divides A or P divides B. Right? So this is a very important lemma, sometimes called Euclid's lemma. And if P divides a product of two numbers, then it divides one or the other of them, or both. And the proof, so given this, so now we want to prove if P divides a product of any number of integers, A1, A2, up to A sub R, then P divides at least one of them. So P divides A sub I for some I. And the proof, so this is a product of R integers. So the proof will be by induction on the number of factors R. So of course, for R equal 1 is trivial. If R equal 1, this says that if P divides A1, then P divides A1. Well, that's kind of obvious, right? So we don't have to say anything about that. For R equal 2, this says if P divides A1 times A2, then P divides A1, or P divides A2. But that's exactly the proposition, 1.619. If P divides a product of two numbers, it divides one of them. So we know this statement is true for R equal 2. So suppose we let R be at least 3 and assume that the statement is true for R minus 1 integers. Right? This is the induction hypothesis. So suppose P divides A1, A2, AR minus 1 up to A sub R, this product of R numbers. Well, I can call the first R minus 1 of them B. So suppose I let B be A1, A2 up to A sub R minus 1. So then P divides B times AR, because B is this product. And so, but now we just have two factors. So P divides B or P divides AR. If P divides AR, we're done. But if P divides B, that means P divides A1 up to A sub R minus 1, because that's what B is. But here we have only R minus 1 factors. So P divides AI for some I from 1 up to R minus 1. So in both cases, P divides one of the factors. And so what we proved is that if the statement is true for a product of R minus 1 factors, then it's true for a product of R factors. That's induction. We proved by the principle of mathematical induction that the statement is true for all R. So this is a very important exercise in understanding how to prove something by induction, which you absolutely have to learn in algebra, and is definitely part of I mean, it will definitely be the case. There'll be some proof involving induction on the midterm and also on the final.
Thank you, Professor.
Sure. Any other questions about homework or anything else?
Professor, would you also go over question number 8 for the
In the
same
same
chapter?
section?
Mm-hmm. Yes.
Okay.
Thank you.
Okay, so let me come back to that because I want to see in exercise 8, it says use the existence of S and T such that something happens. So let me just prove that statement, and then I'll go back and do the exercise. Okay.
Okay, no problem.
All right. So So let's just review a little bit about what we did last week. By the way, that remind you, next Monday is President's Day. College is closed, there are no classes. But next Tuesday, we follow a Monday schedule. So next week, there are classes on Tuesday and on Wednesday, right? So Monday, school was closed. Tuesday follows a Monday schedule, and Wednesday is back to normal. So Wednesday is Wednesday, right? So suppose we have integers, m and n, and we define a set I of m and n, which is the set of every number you can write in the form am plus bn, where a and b run through the set of all integers. So this is what one would call a linear combination of m and n with integer coefficients a and b. And so, and we proved on Wednesday, that is last week already, prop 1.6.9, which says that this set has some nice properties. First, if x and y are in this set, then x plus y is in the set, and x minus y is in the set. So I can write x plus or minus y is in the set, or it's essentially the same thing. If x is in the set, then minus x is in the set. And if b is a common divisor of m and n, not necessarily the greatest common divisor, but if b divides m and b divides n, then b divides x for all x in this set I. So, and again, the reason for that is pretty easy to see. What does it mean to say p divides m? That means m is q1 times b for some q1. And if b divides n, n is q1 times q2 times b for some integers, q1 and q2. So if I take anything, any element of I of, so if x is in I of mn, then x is some linear combination. Let me write it as cm, or let me say rm plus sn for some m and n, but m is q1b and n is q2b. And if I factor out the b, I get rq1 plus sq2 times b. So x is a multiple of b, and that's the whole proof. Right? And what's very important is lemma 1.610. It says if D is a common divisor of M and N, and D belongs to the set I of Mn, then in fact D is the greatest common divisor of M and N. And the proof, well, if D is a common divisor and it's in this set, why is it the greatest common divisor? The reason is if D prime is any common divisor of M and N, we just proved that every common divisor of M and N divides everything in this set I. And D is an I, so D prime divides D. So every common divisor of M and N divides D. So this D is the greatest common divisor. Okay. So again, this is, these proofs are short, but they are dense in the sense that they require a lot of thinking. Now, how do you find the greatest common divisor? So there is something, and again, some of this stuff, though it seems rather sophisticated, goes back to the Greeks. And there is an algorithm called the Euclidean algorithm to compute the GCD, the greatest common divisor of any two integers, M and N, positive integers. Now, if you have taken a course in computer programming, very likely something you did in class or something that was in your book or something that you had to do for homework was to actually write a computer program for the Euclidean algorithm, because it is an algorithm. It's something that can be translated into any computer language and run on your favorite computer using your favorite programming language. And the key is just the division algorithm. Division algorithm says if you take a number M and divide by N, you get a quotient Q and a remainder where the remainder is non-negative and strictly smaller than what you're dividing by. Right? That's the division algorithm. So suppose we take M. So we want to find the greatest common divisor of M and N. We need a process that is completely rigid. There's no thinking involved. It's just automatic, because computers don't think. Computers just follow instructions. So take M, divide it by N, you get a quotient Q1 and a remainder I'll call N1. So N1 is strictly less than N, because it's the remainder when you divide by N. I'm just going to leave some space here, and greater than or equal to 0. Then I take N and I divide by the remainder. I get N is Q2N1 plus the remainder I'll call N2. And N2 is strictly less than what you're dividing by. So N2 is less than N1, but it's still greater than or equal to 0. And then I take N1 and divide by N2, at least, unless I get a 0. If I have a 0 remainder, I stop. But if the remainder is not 0, I can divide by it. N1 is Q3N2 plus N3. And N3 is strictly smaller than N2 and greater than or equal to 0. And I keep iterating this process. When I've done this k times, I have N sub k minus 2 is Q N sub k minus 1. Sorry, N sub k minus 1. No. And this is boom, 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 boom. when I've done this, when I do the kth division, nk minus 2 is qk nk minus 1 plus the remainder, which is n sub k. And n sub k is strictly smaller than everything that came before and greater than or equal to 0. But now this is the important thing. As I do one long division after another, the remainders are strictly decreasing positive integers greater than or equal to 0, which means eventually I have to get a remainder of 0. You can't have infinitely many positive integers strictly decreasing. Eventually, you have to hit 0. So eventually you get to a point where n sub r minus 1 is q sub r plus 1, n sub r, and a remainder of 0. Right? Let me just do an example. So suppose I take m equal to 792. I'm just making up some numbers. We'll see what happens. And n is 315. And I want to find the greatest common divisor of these two numbers. So let's see. So I take 792. If I divide by 315, that has a quotient of 2. This is 630. And it leaves a remainder 630, a remainder of 132, I think. Oops, no. 330, 162. Okay. So this is the first quotient. This is the first remainder. Then I take 315 and I divide by the remainder. 315 is 1 times 162. And what is the remainder? Can someone tell me? What is the remainder when you divide 315 by 162? Okay. All right.
It would be 1.9.
Sorry? No, a remainder. It's an integer. It's long division. Only whole numbers, and no fractions. If you divide 315 by 162, the quotient is 1, and what is the remainder?
Is it 9?
What?
Is it 9?
9 is 162 plus 9 equal to 315? What is, no, obviously not. 162 plus 9 is 171. It's not 315.
Is it 153?
Yes, you just subtract 153, right?
Oh, got it, yes.
162 plus 153 is 315. Right? And now you take 162 and you divide by 153. That goes in one time. And what's the remainder?
9.
9. 153 plus 9 is 162. Take 153 and divide by 9. What is the quotient?
144.
What is the quotient?
Oh, the quotient? Is it 144?
No,
No.
the quotient is 153 is something times 9 plus a remainder. So the quotient is the number that goes here. That's the quotient. This is the remainder.
I think it's 3. No.
3 times 9 is 27. That's
It's 17. It's 17.
17.
Okay.
Plus, all right. And what is the remainder?
0.
0, exactly. So finally, we get a remainder of 0. So if you look at the successive remainders, these are the remainders. We divided by 315. The first remainder was 162. The next, and they have to be getting smaller. The next remainder was 153. The next remainder was 9. And then the last remainder is 0. So the last positive remainder is 9. And you see, this says 9 divides 153. And if 9 divides 153, it divides 162. If 9 divides 153 and 162, it divides 315. If 9 divides 162 and 315, it divides 792. So in this example, we see 9 is a common divisor of 792 and 315. But if you take any common divisor of 792 and 315, if it divides this and this, it divides this, 162. If it divides this and this, it divides 153. If it divides this and 153, it divides 9. So every common divisor of these two numbers divides 9, which means 9 is the greatest common divisor. This is an example of the Euclidean algorithm in operation. And so this is an important example. I mean, you have to, there's an example in the text with bigger numbers that are harder to follow, but this is a simple example, right? So this is exactly what the Euclidean algorithm says to do in general. Take positive integers m and n, divide m by n, you get a remainder n1. Divide n by n1, you get a remainder of n2. Divide n1 by n2, you get a remainder of n3. Divide n2 by n3, you get a remainder of n4, and so forth. And this sequence of remainders is strictly decreasing. They're non-negative integers. So eventually you have to get to 0. And the last positive remainder is the last number you're dividing by, this n sub r. This is a common divisor and the greatest common divisor of m and n. So the Euclidean algorithm says to compute the greatest common divisor of two numbers, simply calculate successive long divisions until you get to 0. And the last thing you're dividing by, or the last positive remainder in that sequence, is the greatest common divisor. So suppose I take the numbers m equal to 4004 and n equal to 3066. Use the Euclidean algorithm. I want you to use it right now. Use Euclidean algorithm to compute the GCD of these two numbers. And send me your answer in the chat. So I want everyone to do this calculation and send me your answer right now. And if you have a question, just ask me along the way.
Okay, sure. Professor, after we're done with this one, would you be able to go through question number 11 and 12 for chapter 1.5?
Oh, let me finish talking about this section, and then at the end of the class, I'll go back to them.
Okay, perfect. Thank you.
And let me pause while you're working on the problem. All right. How do we do this? Here are the two numbers, 4004, 3066. So take 4004. If you divide, right? I mean, you're really, it's just long division. 3066 divided into 4004, it goes one time. And leaves a remainder of 938. So this is 1, that's the quotient, times 3066, plus a remainder of 938. All right. This is where the remainders will be. All right. So now I take 3066, I divide by 938. 938 into 3066. So this goes 3 times. 3 8s are 24, 3 3s are 9, 11. 3 9s are 27, 28. Sorry, 3 8s are 24, 3 3s are 9, plus 2 is 11, 28. So this leaves a remainder of 2, 5, 2. Is that right?
That's what I got. 252.
So 3 times 938 plus 252. Then I take 338 and I divide it by 252, right? So in this column, we're writing the quotients. So 252 into 938 goes 3 times. 3 2s are 6, 750. 8 times 6 is 2. 13 take away 5 is 8, plus 182. Sorry, this goes in 3 times and leaves a remainder of 182. Then you take 252 divided by 182, that goes in once and leaves a remainder of 70. 182, if you divide it by 70, that goes 2 times. 2 times 70 is 140, so that leaves a remainder of 42. You see, these remainders are positive and strictly decreasing. Divide 70 by 42, that goes once and leaves a remainder of 28. Take 42, divide it by 28, the quotient is 1 and leaves a remainder of 14. Take 28, divide it by 14, that goes 2 times, and that leaves a remainder of 0. So these remainders are strictly decreasing, and the last positive remainder is 14. So the GCD, the greatest common divisor of the two numbers I started with, 4,004 and 3,066, is 14. All right. That's the Euclidean algorithm. Any questions about this? This is really very basic for us. Now, if this is the Euclidean algorithm right here, and if you look at this, if you have M and N, it says that N1 is M minus Q1N. So N1 belongs to that set I of Mn that I constructed. But if N and N1 belong to the set, so does N2. If N1 and N2 belong to the set, so does N3. Step by step, so does this last positive remainder. So what that tells us is that the GCD of M and N is in the set I of Mn, which is all linear combinations, Am plus Bn, where A and B are integers. So this set contains the greatest common divisor of the generating numbers M and N. And so this is in the set, and it has to be, in fact, the smallest element of the set, because any smaller element in the set, let's see, why is it the smallest element? If you have every element in the set is divisible by this number, let's call this D, the greatest common divisor of M and N. So every number in this set is divisible by D. And if you had a smaller element in the set and it were divisible by D, it would have to be 0. So this is, in fact, the smallest element in this set. And here we have another important definition. Positive integers M and N are called relatively prime if their greatest common divisor is 1. So, for example, 14 and 15 are relatively prime, because the only number that divides both of them, the only positive integer that divides both, is 1. Or, for example, 37 and 101 are relatively prime. "38 and 57 are not relatively prime." Why is that? Because 38 is 2 times 19. 57 is 3 times 19. So the greatest common divisor of 38 and 57 is at least 19. In fact, it is 19. But what's important is it's greater than 1. So if the GCD is greater than 1, then the numbers are not relatively prime. Two numbers are, this is just a definition. Relatively prime means the GCD, the greatest common divisor, is 1. Right? And because the greatest common divisor of M and N is an element of the set I of Mn, and if the greatest common divisor is 1, that means you can write 1 as AM plus Bn for some integers, for some integers A and B. So this is really a fundamentally important fact. If the greatest common divisors of two integers is 1, then you can write 1 as some integral linear combination of them. And conversely, if 1 is an integral linear combination of M and N, then any number that divides M and N divides 1, and the only positive integer dividing 1 is 1. So this is really an if and only if statement. So two integers are relatively prime if and only if the greatest common divisor is 1. And you can actually use the Euclidean algorithm to find an expression of this sort. So let me look at this example I had a moment ago of 37 and 101. Let's use the Euclidean algorithm to compute their greatest common divisor. So let's take 101. If you divide it by 37, that goes 2 times. 2 times 37 is 74. So this leaves a remainder of 27. 37 is 1 times 27 and a remainder of 10. 27 is 2 times 10 and a remainder of 7. 10 is 1 times 7 and a remainder of 3. 7 is 2 times 3 and a remainder of 1. 3 is 3 times 1 and a remainder of 0. So this tells us that 1, by the Euclidean algorithm, 1 is the greatest common divisor of these two numbers. So let's use this and work backwards. This says that 1 is 7 minus 2 times 3. But this says that 3 is 10 minus 7, which is 7 minus 2 times 10 plus 2 times 7. 2 times 7 plus 7 is 3 times 7. So 1 is 3 times 7 minus 2 times 10. It just says 21 minus 20 is 1. Okay, that's good. And according to this, 7 is 27 minus 2 times 10. So this is 3 times. 7 is 27 minus 2 times 10 minus another 2 times 10. So this is 3 times 27 minus 3 times 2 minus 6 times 10 minus 2 minus 8 times 10. This says 10 is 37 minus 27. So this is 3 times 27 plus 8 times 27. 3 and 8 is 11 times 27, minus 8 times 37. And finally, this says 27. 27 is 101 minus 2 times 37, minus 8 times 37. So this is 11 times 101. 11 times 2 is 22, minus 22 minus 8, minus 30 times 37. So if I've done the arithmetic correctly, and I don't know if I did, so I'll have to come back and check. But this says that 1, which is the GCD of 37 and 101, is 11 times 101 minus 30 times 37. So I've expressed the number 1 as some linear combination of 101 and 37. Let's see. Let's just check. 11 times 101 is 1111. 37 times 30, 3 sevens are 21. 3 threes are 9, 11 is 1110. And 1111 minus 1110 is 1. So this checks. This is correct. Right? So 1 is this integral linear combination of 101 and 37. That's kind of cute. Any questions about this? There's really a lot of material that we're covering. It's in some sense arithmetic. We're just adding, subtracting, and multiplying, dividing integers. And we're not dividing integers to get fractions, just dividing integers to get whole number, quotients, and remainders. So there are now several results that we deduce from this fact about relatively prime integers. So let me just repeat this. If the GCD of two numbers A and B are 1, then there exist integers S and T, positive or negative, such that 1 is SA plus TB. And you can write 1 as an integral linear combination of these two relatively prime integers. So we have the following, which is corollary 1.617. If A and B are relatively prime integers, so the greatest common divisor is 1, and if A divides an integer x and B divides x, then in fact the product AB divides x. So I'm using mathematical notation when I write this down, but you should be looking at the book concurrently, and this is all written out in words in the book. So whichever style you prefer, you have both of them. So how does the proof go? So if A and B are relatively prime, then SA plus TB equals 1 for some integers S and T. For some S and T in the set of integers. So if you take this equation and multiply it by X, like this. So X is SAX plus TBX. And X is divisible by A. If A divides X, that means X is equal to, I'm just going to use the notation in the book, alpha times A. And if X is divisible by B, X is also some integer beta times B. So I can write X as beta times B, and I can write B here as alpha times A, and I can factor an AB out of this. This is AB times the integer S beta plus T alpha. So AB divides X. So if two relatively prime integers divide X, so does their product. And we can make another observation from this. Suppose P is prime and A is just any integer. Suppose we let D be the greatest common divisor of P and A. So D divides P, which means either D equals 1 and P and A have greatest common divisor 1, or D equals P, because P is a prime. Its only positive divisors are itself and 1, P and 1. And then P is the greatest common divisor of P and A, so P divides A. So this is proposition 1.618. It simply says that if you take any two numbers, if you take a prime and any number A, either P divides A or P and A are relatively prime. And now we come to a very important proposition, which is what I mentioned earlier, what is called Euclid's lemma. So that's not the name that the book gives it. So P is a prime and AB are non-zero integers. If P divides the product of two numbers, A and B, then P divides A or P divides B. And the proof is very lovely. So P divides the product A and B. If P divides A, we're done. If P does not divide A, then the GCD of A and P is 1. And so you can write 1 as some linear combination of A and P. So 1 is equal to SA plus TP for some integers S and T. Multiply this equation by B. You get B is SAB plus TPB. But we're told that A divides B, P divides AB. So AB is Q times P for some quotient Q. So B is equal to S Q times P plus, let me just write this, TB times P. If I factor out the P, I get SQ plus TB. So P times this integer is B. So P divides B. Again, these are short proofs, but they're very clever and very interesting.
Professor, we can only use this when the greatest common denominator is 1. Or the greatest.
Sorry, use what?
This like 1 equals SA plus TP.
Yeah, not
Equal-
greatest common denominator, greatest common divisor.
Divisor, I'm sorry.
Yes. But it's true in general, if the GCD of two numbers M and N is D, then you can always write D as AM plus BN. The greatest common divisor of two integers is always a linear combination with integer coefficients of the two integers. Okay, so now we've reached the point I wanted to get to, which is I can now prove what is called the fundamental theorem of arithmetic, which says the prime factorization of an integer is unique up to order. That is, we proved last week that every positive integer greater than 1 is a product of prime numbers. And you can rearrange the prime numbers, like 6 is 2 times 3 or 3 times 2. But other than rearranging the order in which you write the primes down, there's no other way to factor an integer into a product of primes. That's the fundamental theorem of arithmetic. The fact that you can factor an integer, into primes, we proved. But now we have to prove it's unique. So here, this is uniqueness. That's the important thing. Suppose we have an integer n, and we can write it as a product of r primes, and we can also write it as a product of, say, s primes. So these are r primes, and here we have s primes, and we must show that, in fact, the number of primes on both sides of the equation is the same, r equals s, and once you rearrange it, q1 is p1, q2 is p2, and so forth. Q sub r is p sub r. That is, these are exactly the primes in some order. And of course, yeah. So let's prove this by induction. If you take n equal 1, this is a product of no primes. There's only one way to write it, 1 equals 1. If that's too simple, it's supposed to be write n equals 2. So 2 is 2. And suppose we write this as a product of primes, but in fact, because 2 is a prime, its only divisor is itself in 1. So if 2 is a product of these primes, all of these primes divide 2. So each of these primes has to be 2, and there can only be one of them, right? So in that kind of trivial case, it's also true. So now let's look at the general case. Suppose n is q1, q2 up to q sub r, and p1, p2 up to p sub s. So q1 divides n, right? Because if n is this product, n is q1 times the product of these other primes. So q1 divides n, but this is n. So q1 divides p1, p2 up to p sub s. It divides this product. But if a prime divides a product, it divides one of the factors. So q1 divides p sub I for some I. But the only number bigger than 1 that divides a prime is itself. So p sub I is equal to q1. So here I have this number pi, and this number equals this number. So I can divide by it. I get that n over q1 is q2 up to qr, and it's the product of these other primes, p1 up to ps, with p sub I omitted. But n over q1 is less than n. It's n divided by something bigger than 1. So by the induction hypothesis, every number less than n is uniquely a product of primes. So the number of primes here equals the number of primes here, and they have to be exactly the same prime in some order. So that is truly the proof. But you need to spend, I think, a lot of time. I mean, more than a few minutes. You need a lot of time, and I would say on successive days, not all on the same day, trying to understand this proof. The arguments are important. And once you get to these 300 level math classes, it's not like calculus where all you have to do is compute the answer numerically to some problem. Here you have to understand the proofs and be able to give your own proofs. I mean, you have to do calculations. If I give you two numbers and say use the Euclidean algorithm to calculate the greatest common divisor, you need to be able to do that. But you also need, and it's equally important, if not more important, to understand the ideas in these proofs. Okay. All right. There's a tiny bit more in this section, but basically we've covered all of section 1.6. Someone asked, are there any questions about this? Oh, this bit of prime numbers and what is the fundamental theorem of arithmetic? Someone asked me to do some problems in section 1.5, which I am happy to do now if you tell me which problems.
It was question number 11 and 12.
In 1.5. Okay.
Yes.
Sorry, I didn't understand what you said.
Oh, sorry, there is some background noise.
Oh, okay. So, exercise 1.511. Is that the one you asked for? One 1.511. Let me just start to do that. So suppose you take a deck with 2 cards. So you have 1 and 2. That's your deck. And what is a perfect shuffle? You take the deck, you divide it perfectly in order. You put the top half on the left. So if you divide this in order, then you have 1 and 2. Right? On the left, you have the card 1. On the right, you have the card 2. And then you interlace the cards with the first card from the right going on top. So this goes to 2, 1. So here you have a permutation where 1, 2 goes to 2, 1. So as a cycle, this is just the cycle 1, 2. This is the case when you have 2 cards. Suppose I have 4 cards. If I cut it in half, I have 1, 2, and 3, 4. And when I put them back together, when I shuffle them, right, left, 3, 1, 4, 2. So in this shuffle, as a permutation, 1 ends up in the second position, 2 ends up in the fourth position, 3 ends up in the first position, and 4 ends up in the third position. So as a cycle, this is the cycle 1, 2, 4, 3. Let's take a deck. So this is with 4 cards. If I take a deck with 6 cards, if I cut it perfectly, I have 1, 2, 3, 4, 5, 6. When I shuffle them, I go 4, 1, 5, 2, 6, 3. So as a cycle, 1, 2, 3, 4, 5, 6. 1 ended up in the second position, 2 in the fourth, 3 in the sixth, 4 in the first, 5 in the third, 6 in the fifth. So as a cycle, this is 1 goes to 2, goes to 4, goes to 1, 3 goes to 6, goes to 5, goes back to 3. Right. And you can do 12, 14, and 16 without too much trouble. I would skip 52 because that's a very big calculation, though you might see a pattern that makes it a lot easier to figure out. In fact, you can almost see the pattern here. Well, maybe it's not so clear. 1, 2, 3, 4, 5, 6. Well, it is pretty clear, but to find the cycle, you need to do a little bit of calculation. All right. Any questions before we quit for the day? Again, I remind you, we have every week, Wednesday, there's a problem session on Zoom at 1 o'clock. On Friday at 11. On Monday, usually, it's not a holiday, in the evening, and other times by appointment if you contact me. Okay. All right, if there are no questions, then we're done for the day. It's supposed to be 60 degrees today, so beautiful day. Hope everyone gets to enjoy it. Bye all.
Bye.